So this was proved in 1927. So let's let K and R be natural numbers. So then there exists some threshold WRK called the Van de Waerden number, such that whenever n has size at least w, any R coloring of the first n integers, which I'll denote by square brackets around n, contains a monochromatic k-term arithmetic progression. So that will be a configuration of the form x plus y, all the way up to x plus k minus 1 times y. And in this course, like all arithmetic progressions, or more generally polynomial progressions, will be non-trivial. So this just means that y can't be 0, so that this statement is actually interesting. Okay, so this is known as the finitary formulation of Van de Waerden's theorem. So it's finitary because, okay, we have some threshold, and then we're talking about subsets of a finite set. Okay, but this formulation of Van de Waerden's theorem, as you'll prove in the exercises, is equivalent to the following formulation, that if the natural numbers are finitely colored, then some color class contains monochromatic arithmetic progressions of all finite lengths. And you'll see also in the exercises, or I guess you'll show in the exercises, that you can't always find infinite arithmetic progressions. So you'll construct a two-color of the natural numbers containing no infinite monochromatic arithmetic progressions. All right, so in the 1930s, Erudition Turan conjectured that something stronger than Van de Waerden's theorem is true. So they conjectured that in any positive density subset of the natural numbers, you can find arbitrarily long arithmetic progressions, so that Van de Waerden's theorem should hold simply because in any R coloring of the natural numbers, some color class must contain at least a 1 over R proportion of all natural numbers. Okay. So this conjecture of Erudition Turan was proven first for 3-term progressions by Roth in the 1950s, and then in general by Szemerédi in 1975. So the result is known as Szemerédi's theorem. Okay, so like Van de Waerden's theorem, there's an infinitary statement and a finitary statement, and they're equivalent. Okay, so I'll give you the infinitary statement first. All right. So Szemerédi's theorem states that any subset, say A, the natural numbers, having positive upper density, meaning that the lim sup of its density in the first n integers is positive. Okay, so any subset of the natural numbers with positive upper density contains arithmetic progressions of all finite lengths. So this statement is equivalent to the following finitary statement. Okay, so let's let k be the length of our progression. Okay, so then if, or maybe I'll formulate this as, then we have that the maximum size of a subset of the first n integers containing no k-term arithmetic progressions is little o of n. So maximum size of A such that A is contained first n integers has no k-term arithmetic progressions. This quantity is little o of n. Okay, so now I'll say something about asymptotic notation. So whenever some sort of asymptotic symbol appears with a subscript, then either the implied constant or, in this case, the rate at which this quantity divided by n tends to 0 may depend on the parameters in the subscript. Also, throughout this course, I'll be using Vinogradov's asymptotic notation. Which is standard in analytic number theory. So if I write x less than y, I mean x is big O of y. And if I write like x greater than y, for me that means x is big omega of y. So bounded below by an absolute constant times y. And then I write x, I don't know what this is called except y. So this means that y is less than x, which is less than y. So they're asymptotically like the same order of magnitude. Okay. All right, so after Szemerédi proved his theorem, Furstenberg gave an alternative proof a couple years later via ergodic theory. And out of all of the proofs of Szemerédi's theorem that we have now, Furstenberg's proof is still by far the most flexible and amenable to generalizations. And has been used to prove some like very, very broad generalizations of Szemerédi's theorem that we have like no other proofs of. And one of these is the multidimensional polynomial Szemerédi theorem of Bergelsen and Leibman. Okay, so I'll state not quite its most general form, because its most general form is hard to parse. I'll state the almost most general form. This was proved in 1996. Okay, so for this, let's let first P1 up to Pm be polynomials with integer coefficients with 0 constant term. So pi of 0 equals 0. And let's say we have vectors v1 up to vm in z to the d. Okay, so then we'll have a similar statement, but for sets lacking multidimensional polynomial configurations. So I'll state this as if A is a subset of the d-dimensional integer grid, side length big N, and it has no non-trivial polynomial, I won't fit that, no polynomial configurations. So x plus p1 of y times the vector v1. Okay, so this is in z to the d, and v1 is in z to the d. And then this is just a scalar, all the way up to x plus pm of y, vm. okay, with y not equal to 0. But you can actually forbid kind of like any finite number of y, or any finite number of possible y's. So you could also state this with forbidding like any roots of like any of these polynomials. So if A has none of these polynomial configurations, then okay, size of A is little o, depending on the polynomials, the vectors, of the trivial bound n to the d. Okay. So I'll give some examples of configurations that this theorem applies to. Okay, so, well, first of all, it applies to the case of k-term arithmetic progressions. Okay, so we can recover Szemerédi's theorem by taking like d to be 1, the polynomials to be like y up to k minus 1 times y, and then like the v's to just be 1. And then this configuration is exactly a non-trivial k-term arithmetic progression. So if we stay in one dimension but want nonlinear polynomials, then this theorem also applies to finding the configuration known as the nonlinear Roth configuration. So it's like a 3-term arithmetic progression, but instead of 2y, we have y squared. Okay. So if you specialize to the case of linear polynomials, then you get what's known as the multidimensional Szemerédi theorem, and this was proven by Furstenberg and Katz-Nelson a couple years after Furstenberg gave his ergodic theoretic proof of Szemerédi's theorem. So for example, this theorem tells you that in any positive density subset of z cross z, you can find 4 vertices of an axis-aligned square. So you can find the configuration xy, xy plus d, x plus dy, x plus d, y plus d. You can also mix multidimensional and polynomial configurations. So this also applies to what are called now scorners. Okay. This was not my idea. Okay. So it's like a corner, which would be x comma y plus d, x plus d comma y, but instead in the vertical direction, or I guess, sorry, this is horizontal direction, you shift by the square of the parameter d. Right. So it's a major open problem in the area to give a proof of this theorem that doesn't use ergodic theory. So all of these proofs by ergodic theory give you like no explicit bounds for this little o of n to the d term. So like not even like in principle, it's not even like we get some like super bad one. And so it's like even an open problem to give like just some explicit bounds in this theorem. But ideally, we would like a more combinatorial proof of the Berghuis-Leibman theorem that gives a reasonable bound for the size of A. And by that I mean a savings over the trivial bound of n to the d by like some finite number of iterated logs of n. Okay. So reasonable bounds are known. Now for k-term arithmetic progressions, they're known for the nonlinear Roth configuration. They're known for scorners. And like a small number of other special cases, they're not known for sets lacking axis-aligned squares. So this is my favorite problem. And so I'll just state a couple of these theorems with their bounds. So for k-term arithmetic progressions, reasonable bounds were actually obtained in this first proof by Roth for 3-term progressions, which was in 1953. And then reasonable bounds in Szemerédi's theorem for longer progressions weren't obtained until work of Gowers in 1998 for 4-term progressions, and then 2001 for progressions of all lengths. Okay, and bounds obtained by them save you log-log. Okay, so if A is a subset of the natural, or the first n integers, and it has no k-term arithmetic progressions, then the size of A is bounded above by some constant times n over some power of log n. That depends on k. Okay. So this bound has now been improved. Okay, but that's outside of the scope of this course. And Sean Prendeville and I were the first to prove reasonable bounds, I guess any bounds at all, for the size of sets lacking the nonlinear Roth configuration. Okay, so we did this in 2019, okay, but it was published last year. So we showed that if A is a subset of the first n integers, and it has no nonlinear Roth configurations, then size of A is also bounded above by like n over some power of log. Okay, and actually the constant we get is 2 to the negative 2 to the 157 or something. Okay. But we can now improve this to like n over a similar power of log. So the goal of this course is to like prove this theorem from scratch, and along the way introduce you to several like fundamental techniques in additive combinatorics. Right. So, okay, did I want to say anything else before? Yeah. So before I talk about the proofs, I'll give you a bit more notation that I'll use frequently. Right, so first of all, for any function f from a set S to complex numbers, where S is finite and non-empty, we'll write big E to note the average of f over S, so little s and big S, f of S. This is 1 over size of S, sum over S and big S, f of S. Okay, I'll also denote indicator functions with a 1, not a chi. So for T any set, indicator function of T, okay, this will be 1 when x is in T, 0 otherwise. I guess that means x not in T. Finally, I'll use what is standard notation in analytic number theory. So for any complex number z, we'll write E of z to be e to the 2 pi I z. And then additionally, for any natural number q, E sub q of z is E of like z over q. Okay, so this function is like Q periodic. So this also defines, or this also gives a well-defined function on the integers mod Q. Basically, okay, so for the first like lecture, okay, Q will always be P, a prime. And okay, so that's all I need before I start telling you about the first proof technique, which is repeatedly applying the Cauchy-Schwarz inequality. Okay, so to set this up, so we can also ask for reasonable bounds in the multidimensional polynomial Szemerédi theorem when we replace the d-dimensional integer grid with like some other sets, as long as it makes sense. So we can replace, in particular, the natural numbers from 1 up to n by a finite field. Because if you have a polynomial progression in the integers or in z to the d, and you reduce it mod p, then you'll get one in fp or in like fp to the d. So if you were able to get reasonable bounds in like the integer setting, you could get them in the finite field setting, but we can hope that the finite field setting is easier, and that turns out to be the case. So for the remainder of this lecture, we will replace the integers from 1 up to n with fp, and then we're interested in the regime where p tends to infinity. So before Sean and I proved our theorem, Waerden and Chang had proved the finite field version of it. So this is a theorem of Waerden and Chang. From 2017. Okay, so it states that if A is a subset of fp, and it has no nonlinear Roth configurations, so it has no configurations of the form x plus y squared. Then they actually obtain a power-saving bound for the size of A. So then A has size at most p to the 14 over 15. So as first I'll say that this exponent, 14 over 15, has now been improved actually a couple of times. So now the best known upper bound is like p to the 7/8. They actually prove a stronger statement. So they actually prove a mixing version of this theorem. Okay, which says that if A, B, and C are all possibly different subsets of FP that are all sufficiently large, I'll just say are all sufficiently large. So all just have to be greater than some like fractional power of p. Then there exists a pair x and y such that the first term of the nonlinear Roth configuration is in A, the second term is in B, and the third term is in C. Okay. Yeah, so note that you definitely cannot prove something like this for a 3-term arithmetic progression. Yeah, but somehow the nonlinear polynomial situation has more mixing going on. Right. Okay, so they prove their theorem via Fourier analysis, using that you can explicitly evaluate some objects in number theory called quadratic Gauss sums. And their method does not extend to other polynomial configurations or to the integer setting. And yeah, actually realizing that and reading this paper is how I got into this topic in the first place. So we're not gonna prove this, except, well, I guess we'll prove a weaker quantitative version that implies it later. But instead, today we're going to discuss a result of Shkredov. From 2010 that also proves a mixing result for another configuration that mixes both like addition and multiplication. Okay, so for this, let's let A, B, and C be subsets of FP. And let's assume that the product of their sizes is at least some constant times P to the 5 halves. Okay, note that the trivial upper bound for this, so each one of these can have size at most P, would be like P cubed. Okay, so this is like a bit of a power savings. So then there exists some pair X and Y in FP, such that x plus y, x times y, is in A cross B cross C. So in particular, if you have any sufficiently large subset of FP, you'll obtain a configuration of the form x plus y, and x times y in that set. So Shkredov's original proof, like the proof of Waerden and Chang, is Fourier analytic. But I'll present for you a proof that is like just repeated applications of the Cauchy-Schwarz inequality. So actually, we'll obtain this statement just for ease of exposition. We'll prove this with P to the 5 halves replaced by slightly larger P to the 11 over 4. But in the proof I give, if you're more careful and you keep track of like L2 norms that appear when doing Cauchy-Schwarz's, then you can recover basically exactly Shkredov's theorem. So I put this first because repeatedly applying the Cauchy-Schwarz inequality is, I think, like the most important skill to have in like this part of additive combinatorics. Like you can prove like remarkably strong things if you know how to cleverly apply the Cauchy-Schwarz inequality and change variables like over and over and over again. Okay, so yeah, now I'll talk about how to prove this. The slightly weaker bounds. Okay. Okay, so set some notation. Let's let f, g, and h be some functions from fp to complex numbers. Okay, so then we'll define a trilinear counting operator, lambda f, g, and h, which will just count the number of these configurations weighted by f, g, and h. So this will be the average over x and y in FP of f of x, g of x plus y, h of x times y. Okay, so then note that, first of all, this is a trilinear function of f, g, and h. Just because this is average, yeah, trilinear function of f, g, and h. And we also have for any subsets A, B, and C in FP, if you plug in their indicator functions, you get the normalized count of these configurations in this Cartesian product. So the number of pairs x and y such that x, x plus y, x times y is in A cross B cross C, divided by the normalization p squared. So that's the total number of x's and y's. Okay. So to deduce Shkadov's theorem with this slightly worse exponent, we will show that the following key theorem holds. Okay, so this is, you can view this as a mixing theorem. Okay, so for this, let's let f, g, and h be any functions from fp to the complex numbers that are one-bounded, meaning that their modulus is always bounded above by 1. Then, okay, here's why I call this a mixing theorem. Lambda of f, g, and h equals the product of their averages plus some small error. So this equals the average of f, average value of g, times average value of h, plus an error that's like big O of 1 over p to the 1/4. Okay, so then it's an exercise to see why this mixing theorem implies Shkadov's theorem with 5/2 replaced by 11 over 4. Okay. So to prove this, we first reduce to the case that G has mean 0. So we want to reduce to studying lambda of f, g, and h when G has mean 0. This is a simple consequence, basically, of the trilinearity of lambda. Okay, so first we'll show I lost the chalk. This seems like a new one. Whatever. Oh, it's here. Okay. All right, so first, we'll show that if f, g, and h are one-bounded functions, then lambda of f, g, and h, so this equals the main term we want, so the product of the average value of f, the average value of g, the average value of h, plus the term lambda f, g minus the average of g, h, plus an error that's big O of 1 over p. Okay, so note that because we've subtracted off the average value of g, this now has mean 0. Okay. Yeah, so this is what we wanted to reduce to this situation. So once we prove this, then all one needs to prove the mixing theorem is to bound the size of this counting operator when g has mean 0, and like f, g, and h are all one bounded. So the proof of this is not hard. There's no Cauchy-Schwarz yet. So we write g as g minus its average value plus its average value. And then we use that lambda is trilinear. So then we have lambda of f, g, and h. Then this is like lambda of f, g minus its average value, h, plus lambda of f, the constant function, that's just the average value of g, h. Okay, so then we have this first term, which is one of the terms we want. Plus the average value of g times lambda of f, constant function 1, and h. Okay, so it just remains to analyze this. And we'll see that this is basically the product of the average values of f and h up to a small error. All right, so we have, this is not so, this is just we have. So what is lambda of f1h? Okay, this is just the average over x and y in fp. F of x, h of x times y. So then this is like almost the product of the averages, except when x is 0, then the average over y doesn't take like xy uniformly over all of fp, it just gives you 0. Okay, but so we can rectify this by like restricting the average over x in fp to non-zero x in fp. And we can do that up to an error that's big O of 1 over p. Okay, so I claim that this is the same as the average over x in non-zero elements of the field. It's the average over y in fp of h of xy plus big O of 1 over p. Okay, because the non-zero elements are just off from all the elements by 1, and the normalization factor, p over p minus 1, this is 1 plus big O of 1 over p, and like so is the reciprocal. So we can kind of freely do this maneuver of restricting to non-zero elements or then extending to an average over all the elements at the cost of an error that's big O of 1 over p. Okay, and so, but now I'm happy, because I can make a change of variables. Y maps to y over x in this second average. No, y. Okay, still have our error. And now this is the average value of h. And so now this is almost the average value of f, but we need to extend the average to be over all of fp and pick up another one of these errors. Okay, but that's fine. So this ends up being the average value of f times the average value of h plus big O 1 over p. Okay, so now we can plug that back in to here and get that lambda of f, g, and h is the product of average values of f, g, and h plus, plus this term, plus some error that's on the order of 1 over p at most. Okay, so this completes the proof. All right. Yeah, so now I want to prove the main Cauchy-Schwarz lemma, which will show that if f, g, and h are functions from fp to the complex numbers that are one-bounded, and g has average value 0, then the size of the associated counting operator is bounded above by 1 over p to the 1/4. Okay, so the 1/4 represents doing Cauchy-Schwarz twice. Okay, so let's see how to prove this. Okay, so let's just write out what this is, first of all. So we have that lambda f, g, and h. Just writing out its definition. So this is the average for x and y in fp. F of x, g of x plus y, h of x times y. And then, like in the previous proof, so I only really need to do this for y. Or no, yeah, I only really need to do this for y. But I'm going to do it for x as well, just for ease of notation. I can restrict the average to 1 over x and y non-zero at the cost of an error that's big O of 1 over p. Oh, yeah?
In the previous proof, you used the one problem in this step prior to the change of variables, right? Or is
Yes. Well, yeah. So to restrict this to the sum over non-zero things, yeah, I need that f and h are both one-bounded. Yeah. Okay. So now I'm going to restrict to the case that x and y are both non-zero. Plus I pick up some error, 1 over p. And now I'm going to make a change of variables. I'm going to map x to x divided by y. Yeah, so then I'll make the change of variables. X maps to x over y to get that this is the average over, and I'm also going to rearrange it a bit, the average over x of now, so if I divide x by y everywhere, this will be like h of x. Then I'll have an average over non-zero y. So then I get f of x over y times g of x over y plus y. Okay, yeah, all this plus the error. Okay, so now is when I'm going to apply the Cauchy-Schwarz inequality. Okay, so I'm going to apply the Cauchy-Schwarz inequality with the average over x. And then my first function is going to be h of x. So that's one-bounded. So then the average of like its modulus squared is going to be bounded above by 1. And then the second function will be this as a function of x, so this average over y of these two things. Okay, so then this tells us that lambda of f, g, and h modulus squared is bounded above by so we have the factor 1 coming from the L2 norm of h. And then we get average over x non-zero modulus squared of the average over y squared. And then we still carry around this error. Okay. So now what I'm going to do is like expand this square. So then that gives us like two averages. And so we're going to have an average over y, and then I'm going to call the second copy of y z. So this equals the average over x. Then we have an average over y and z, f of x over y. And then the second copy, which will come with a complex conjugate, x over z. And then g of x over y plus y. And then the second copy, also with a complex conjugate, y replaced by z, plus our error. Okay, so now I'm going to make another change of variables for doing another Cauchy-Schwarz. So I'm going to make the change of variables okay, so this is going to involve changing two of the variables. So we're going to make the change of variables. So first we're going to map x to x times z. And then we're going to set a to be z over y. Okay, so that this is just, yeah, some relabeling. So we get that this equals. Okay, so now we have an average of x, y, and a, non-zero. So what does this one become? So we'll multiply like x by z, and then we call z over y a. So this is just going to be f of x times a. Okay, so then this one, so we multiply x by z. This will be f bar of x. Then what does this become? So we multiply x by z. Then z over y is a. So this is x times a plus y. And then this one becomes, so x times z, so we get x, and then z is, because of this, like y times a. This will be x plus ay. Okay, then we have all this plus our error. Okay, so now we apply the Cauchy-Schwarz inequality one more time. So we're going to fix the variables x and a, and then Cauchy-Schwarz away f of x times f of x times a. So we're going to write it as so no average over y yet. F of x times a, f bar of x times the average over y of these two functions. Plus the error. And so now we'll apply the Cauchy-Schwarz inequality to Cauchy-Schwarz this away, and then double the y variable by squaring that term. So another application. of the Cauchy-Schwarz inequality gives that lambda to the fourth is at most the average over x and a, average over y. Okay, first one doesn't have the bar. Plus some error, like 1 over p. So if we expand this square, then we'll basically be done. So this is the average over x, a, y, and we'll call the new y z. So we get g of xa plus y, g bar of xa plus z, g of x plus ay, g bar, oh no, sorry, this one had a bar. It doesn't matter, but x plus az plus our error. And now the key thing to note is that or maybe I want to do one more simplification. So now we can extend this average to 1 over all of fp at the cost of incurring, because the g's are 1 bounded, like some error that's also big O of 1 over p. Okay, so now this will be xa, y, and z over all of fp. G of xa plus y, g bar of xa plus z, g bar of x plus ay, g of x plus az, plus big O of 1 over p. Okay, so now the key thing to note is that as x, a, y, and z ranges over, as it ranges over all of fp to the fourth, the quadruple of these arguments becomes essentially equidistributed. So this basically becomes equidistributed. Over all of fp to the fourth. Okay, so then this average is actually like very close to the average of like g of x1, g of x2, g of x3, and g of x4 over like x1 up to x4 just ranging over fp. So this should be very close to being like basically just 0. Okay, so you will verify this in the exercises. So to formally state what I mean, let's define for vector c in fp to the fourth, mu of c to be the number of ways as x, a, y, and b range to represent the vector in this form. So this will be the normalized number of x, a, y, and z in fp to the fourth, such that, okay, I'll call this star. This 4 tuple equals c divided by p to the fourth. And then let's also let mu tilde be the uniform measure. on fp to the 4. Okay, so this weights everything by 1 over p to the 4. So then you will show that if you sum over all c, then the mu minus mu tilde, its absolute value, okay, this is on average at most 1 over p. Okay. So now one can apply that here. Okay. All right, so we have lambda of fg and h to the 4th is at most the sum over all c of the product of g of ci, okay, maybe with some complex conjugates. Okay. Let's say complex conjugate so this will be complex conjugate if I is even, or if I is odd, otherwise do nothing. G of ci times the measure mu plus an error that's 1 over p. Okay, but then we can write mu as mu minus tilde, mu tilde plus mu tilde. This will just be the uniform measure. Okay, so by the assumption that g has mean 0, this term is going to be 0. Okay, so since this is a uniform measure, this will just be the average value of g squared times the average value of the conjugate of g squared. Both of those are 0, or all of those are 0. And then the second term, this is bounded above by, since g is 1 bounded, exactly this quantity. So this is less than 1 over p to the 1/4. Oh no, less than 1 over p. And then this was all plus there. Okay, so the upshot is that the absolute value of lambda to the 4th is at most 1 over p. So absolute value of lambda is bounded above by some constant times 1 over p to the 1/4. And in the exercises, I ask you to give, so this is the hardest of the exercises. I ask you to give a similar, like, Cauchy-Schwarz proof of the Bourgain-Chang theorem. And if you can do that, there's a kind of open problem of Freddie Manners to get a Fourier-free proof of the nonlinear Roth theorem with good bounds that Sean and I proved. So I do know how to give a Cauchy-Schwarz proof of the Bourgain-Chang theorem, but not a good enough one to give a Fourier-free proof in the integer setting. Yeah, so now I'm out of time. I'll stop there.